Welcome to another Triton programming tutorial. Today we'll be looking at matrix multiplication. Okay, so we've covered vector addition in one dimensional, we've covered metric addition, that is vector addition in two dimension. Today we'll be looking at a very popular use case, which is matrix multiplication. Okay, so let's get started here. Let's assume that I have a matrix A of dimension mk. So there are m rows and k columns, which is like, for example, let's suppose we have 8 rows and 6 columns, and then we have matrix B, which is k by n dimension, right? K rows and n column. And when you're multiplying two matrices, the number of columns for the first one and number of rows for the second one have to be equal, right? So let's assume we have 8, 6 here, 8 rows and 6 columns, and for the second one, 6 rows and 12 columns. Okay, now the output matrix is going to be, let's say we call it C, is going to be 8 by 12, right? So eight rows and n columns, m by n. So we have mk as input and kn as another input matrix, and then output is m by n, which is 8 rows and n columns. Now let us assume I mean, on the row dimension, we are going to do tiling or parallel computation using the dimensions of C. So it's called tiling and Triton, or you can think of it, each tile is a computation that runs in parallel. So here, let's say I have a block size of 4 and block M size of 4, which means that I'll be dividing the rows into blocks of 4, and then I'll have block N of 6. This is just to show an example, okay? So I have block M, which is 4, and block N, which is 6. So what that means is, for output matrix C, which has 8 rows and 12 columns, I'm going to divide the rows. Since I have block M4, 8 rows will be divided into blocks of 2 of 4, right? So 0, 0, 1, 2, 3. This will be one block, and then the other block is 4, 5, 6, 7. Yeah. So 8. And then I get basically I'm getting two grids on the row dimension because my block size is M. Now, because I have 12 columns and assuming n is 6, so again, right? So I'll have 12 by 6, which means 2. There will be two grids on the y-axis or on the column axis. So the row axis, the size is 4 blocks and the column size is 6 blocks. So here I get 0, 1 on the column, I get 0, 1, 2, 3, 5, and then I get 6, 7, 8, 9, 10, 11 here on the. So yeah, you can think of it each tile as a parallel computation that Triton does. So by tiling, it's a fancy of name of saying some block of computation that is happening. So if you look at this one, my first tile is 0, 0. What that means is PIDM, which is the process ID on the program ID on the row size, it is 0, 0 here, right? And each of these tiles will be of block M by block N size. So because I have 4 by 6, each of this is block M. We call it in short form BM by BN. So BM by BN is 4 by 6 here. And the PID here is 0, comma 0. And then as I move towards right, here it's 0, comma 1, right? So you can see that here PIDM is 0 and PIDN is 0 and 1. So here it's 0, and then we are incrementing the PID 1 as we go towards right, towards the column side. So n is the PID on the column size and m is on the row size. We've covered this in previous video. Okay. Similarly, if we move down on the row side, here the PIDM is going to increase. So you have 1, and then this remains same, right? And each of these, so if you look at this example, you have 6 columns and 4 rows because BM is 4 and BN is 6, and each of these tile will be computed in parallel, right? And how do you index these tiles? With PIDM and PIDN, right? So as you change PIDM and PIDN, you'll have different tiles, and that is what Triton does internally. It supplies you PIDM and PIDN along each dimensional axis, and then you can use that to find out which tile you are in, and then find the offsets and do computation there. So I hope this is clear now. Each of these tile uh, are processed. Each of these tiles is processed in parallel in Triton. Okay, so keep this diagram in mind. Also, when you basically, so this is the output, we are tiling over the output matrix C, right? So but internally, when you our input is A and B, but we are multiplying A with B, you have to remember that, but the tiling is over the output matrix C. Yeah, and then when you multiply A with B in matrix multiplication, you do sum over K, right? Like, so for example, C output C I of J is equal to m input a of I, and then the column, you take all the column for k is equal to 1 to capital K, because we have k here, and then b, you take the first column of b, and then you do the all the rows, right, 1 to k, you go down. So that's what you do in actual mathematics, and we'll see that how it's done in the program. Okay, so now let's look at the code. I just wanted to show you a picture of what is actually happening, and then we'll go to the code part. Okay, so all right. Yeah, so okay, so I'm importing all of these. I've run this, so it's like I'm putting torch, Triton, Triton language is TL. Now this is the main kernel that is being written here. So yeah, you just decorate it with Triton.git, right? And then I'm defining all these parameters. A pointer is my input, B pointer is another input matrix, C is the output matrix, M is the number of rows, N is the number of columns of M is the number of rows of matrix A, N is the columns of matrix B, and K is column of A, and then the row of B, right? So yeah, and the output is going to be M by N. So the input is M by K, and M by K into K by N is equal to M by N. Yeah, so that's what we discussed earlier. Then I have stride AM, stride along dimensional rows, which is AM, and then stride of A along dimensional K. K is the number of rows of matrix A, right? Similarly, stride BK, stride BN, and then the output is M by N, so we have stride CM and stride CN. Okay, right? So then, yeah, and then this is the block size, which is a constant. This depends on you. You can choose whatever you want, right? And we'll see how you can do auto tuning, which helps you in finding the best M and Ks, right? So block M, block N, and then and we also need block K, which I'll explain to you later. When we are doing that summation over K is equal to 1 to capital K, you typically do it in blocks of K, rather than just doing one by one, right? So it helps. Again, this is also done to improve the computation and make it faster. Okay, so after defining all of this, uh, this is the most basic multiplication. We'll look at another one, but yeah, for you, let us go through this. Now, I get the program ID of 0, and then on the x-axis, so I'm calling it PIDM, and then I do the same and get the along the row axis, which I'm calling at PIDN. So I get PIDM and PIDN, which is so a 0 dimension, which is row, and then 1 is on the column side. Okay, so I get all of this PIDM and PIDN, and then we've seen this earlier, right? So each of these, then you have to find the offsets within the tile. So basically, how are you finding? So each of these program is like a tile that I showed you. Now within this, how do you find the offsets? So we do TL arrange block M, right? So you get, and then I'm adding one more dimension called null here. So I get BM by one. So basically, I multiply PIDM into block size, because I know I need to be in which tile, and then I get these numbers. Similarly, PIDN into block N, and then the TLA range block N. So again, I get BM by 1. Here I get an offset of N, 1 by BN. Okay. Yeah, so this is just like what we've even covered this before. So go on incrementing block by block on the x-axis and on the y-axis, and you get each of these. So these offsets are within the tile, okay? Yeah, and then just to make sure that you don't go outside the m and number of rows and columns beyond the limit, you do this thing. Offset of m has to be less than m, and offset of n. And since we are tiling it over the output matrix, we are calling it mass C. Okay, so you make sure you don't cross the number of rows and you don't cross the number of columns. Okay, and then our output is of size block m by block n, right? That's what we discussed. So this is within the tile, right? So it's not going to be m by n directly, because that is your final C. But yeah, within the each tile you have we have each computation of tile size block m block m. So I'm just initializing a output accumulator, like calling it zeros, and then this is a float 32 type. Yeah, that is, yeah. So yeah, then this is a zeros, and now this is what I was talking about. So what you do is you increment k, right? So our output dimension, as I told you, we have an input of m by k and n by and k by n. so when you do multiplication, you loop over all the k columns and the k rows, and then you do. So that's what I'm doing here. But instead of doing one by one, I'm doing it in size of block k. Now this block k also you can choose. It depends on you can choose any value. So okay, so I do this, then I take k0, and then basically I'm finding the offset of k, and just doing some matrix calculation. Yeah, so basically, now a pointer, I get a pointers from offset of m, stride m, and then offset of k that I calculated here. So I get a pointer is of this dimension bm by bk, and then b pointer will be bk and bk, and I'm then going to multiply this. Right, so a pointer into b pointer. So that is what typically is happening. Again, masking is just to make sure that none of these go out, right? Just an extra step. So I get mask A and then mask B, and then I load each of these pointers, TL load, right? The pointers that I calculated here. So I get A and B. Now A and B is of this dimension, Bm by K. Then I finally multiply. So for multiplication in Triton, you have TL dot A and B. So I is going to be Bm into Bk, and then output is going to be this Bm into Bn, right? And that is what I go on adding this, right? This is typically how you calculate how you do matrix multiplication, and accumulator is what I've defined here. So you go on adding this till you get the final output. So for k in range 0 to k in block size of k, and then I go on adding this, and finally when I come out of the loop, when this is all done, that means in the first tile, all the I've multiplied rows and columns, I store it in the output pointer, and this is what I get. So I do C pointer into offset stride, and then store it there. So yeah, I mean the only difference from the addition part is like a little bit is this part that we are when we are doing matrix multiplication in chunks of k, right? So if you look at the math, it's not very difficult. I can show it to you. Yeah, so this is we covered this when we are multiplying. Now that kernel that you saw is actually the tile computation for each of these tile. Now this is the output tile, but to get this output tile, this is typically what happens. Now this is A, right? A is dimension m by k, but on the k side we are picking up in block of k. We are not like so. For example, to get that output on the row side, you have to have k columns, right? So this is how you do. You take k0 all the way till block of k, and then same thing you do on the for the b you go down, so you will have k0 and k this one, and you multiply this this b panel, which is bkn, and this is a panel bm into bk, right? So you take these and then you multiply it with these here, right? Like the row here, and that is what is happening, but you don't multiply it one by one. You do it in block size. So and block cake is can be any number. So that is what is happening within that loop. So I hope you like understand it. Uh, each of these tile is of size bm by bk, and your this k dimension you are breaking it down into blocks of block k, right? So this bk is being broken down into uh, small chunks of block k, and then and you're multiplying it in that loop that you saw there. Okay, so this is what is happening. So this is input a and b, and once you multiply this, you get the output of C, which is the tile here. Okay. Yeah, you have to accumulate it and add it, and then you get that. Okay, yeah. So that's what typically is happening. Now I want to run it and see. So this one is you run the kernel, okay, and then I can run this. So once I have the once I have the multiplication kernel, all I'm doing here is I'm defining some inputs, and I'll pass that, right? So the first thing is uh, I'm making sure that both these my input matrices are on CUDA, right? So making sure that is happening there, and then getting the shape of input, so m by k, and then mk and n from here, and then I'm initializing an empty output of dimension m by n, which is what I'm going to get eventually. And the device has to be same. Okay. Then I define bm, bnk, 64, 64, 62. This number is random, and you can choose whatever you want. All right. And then this is what we have done earlier also. You need to pass a grid. Now, what is a grid is the number of tiles that you're going to have on the row dimension and on the column dimension. So on the row dimension, it's m by bm, right? Return C div is like the ceiling division. So you do m by bm. This is the number of tiles or number of grids you're going to have on the row size. and this is the ones that you're going to have on the column size, n by bn, right? So this is a two-dimensional grid. And also I've mentioned it's on the C output matrix. That's why bm and bn. Okay, so I get this grid, and then this is the final kernel I'm calling. This is how you call a kernel, Triton kernel that you define, matmul, this one, right? So yeah, you call that and you pass the grid in square matrix brackets, and then all the arguments, whatever it's needed there. All right, and then finally, I'm getting the output, which is C here. Okay, now let's run this. And then these are the dimension. Now I'm finally defining my A, B, and then I'm calling this output function matmin here, right, which will return to me C. I'm storing C that here, and just for comparison, I'm using torch multiplication and seeing Triton and torch out of both of them are close, right? So I'm doing out. This is output of Triton and this output of torch, and I'm making sure I'm just printing what is the error. It should be ideally zero. So let's run this, right? So I get that, and you see this is almost like 0.000 e to the power 0.5, which is like a very, very small number, which basically tells you that these are equal computation. Okay, now all right, so one of the things I wanted to show you is there is in Triton you can auto tune these parameters. Okay, what that means is now for now I chose these numbers as random, right? My block M, block N, and block K size 64, 64, 32. But how do you know that's the optimal? For that, Triton offers you something called auto tune, wherein you can pass. Okay, so this is how you do when you're defining your kernel here. Everything remains the same. All you do is you can pass this, you can decorate it with another decorator called triton.autotune, and then you pass the config, which is a list of certain parameters that you need to pass. Okay, and in this config you pass triton.config block m, which is again, so you can pass a dictionary block m 64. So I'm saying 64. I'm giving these combinations. Now the first time Triton runs, it will take all of these combination and pick up the fastest, and then cache that as the result for the next computation. So uh, you don't whatever input you give initially doesn't matter. It will pick up the best combination from all of these, and that will become your block M, block N, and block K. Okay, so this is how you do auto return, and then part configs, which is the list, and then you give keys. Key here. What does key mean? That if M and N and K change, then based on these values, you find the most optimal block M, block N, and block K. Okay, and then uh, there are these two things that you can pass. So number of warps means that basically this is to increase your parallel computation. What like within Triton also, the higher the value, the faster the computation will be. But you might like put a lot of pressure on the registers of the GPU. But this is just done to increase the speed. So here I'm saying 4 means like okay, 8 is faster than 4, but yeah, it's like the higher the better, but after a point it just becomes it doesn't increase the speed. Okay, and then number of stages is also an optimization technique, typically for pipelining your software stages. What that means is when you do tl.load and store, it is going to it's going to for memory efficiency, it will combine certain stages. So loading and writing, it's like an internal memory optimization that Triton does. Think of it like okay, when you have more stages, it's going to optimize even more, right? So it basically is going to the loading and computation part, some of it will be uh, merged into each other, or you can call it like pipelined into each other to for memory efficiency. Yeah, so these are you define auto tune like this. Your kernel remains the same. You don't do anything here. All you do is now this block M, block N, and block K will be passed from here, the most optimal values. The logic remains the same. Like there's no difference here. I can like run it and show it to you. Yeah, the kernel remains the same, and then you just here what happens is you can pass some dummy values here. That's what I've done here, block M and block K, but this will be over. Auto-tune will override this, so everything remains the same. You just put auto-tune, and you get a better output. Yeah. Yeah, exactly the same output, no difference, right? So same numbers, but now it's optimally picking up the most optimal value of mm. It's just like a faster computation. We are doing this. All right, so was the simplest form of matrix multiplication. But there are now I want to cover one more concept here, which is called grouping. Grouping is typically done to improve again performance even further. Uh, but yeah, I mean it's not required. but typically you see like matrix multiplication they use grouping. And so this was the most simplest, this was the simplest form of matrix multiplication. Logically this is what is happening, but to use caching in Triton, they use grouping. Now what grouping does is, let me show you in the form of diagram is okay. So here you see your tiling is basically it can go on the 0 1 and then it's going here is 0 0 and then 0 1. Now what they realize is when you try to uh, read columns, right? So you basically columns are on your matrix B, right? So on the n dimension of matrix B, this is rows of B and then columns, right? So you are in matrix multiplication, you're taking rows of A and multiplying it with columns of B. Now what they've realized is to when you read B, you're taking all the columns of B and putting it in caching, putting it in the cache. Now to re you don't want to again load B again and again. So what typically what they want to do, what happens in grouping is you want to use the L2 cache of on the basically the column. You want to bring in the columns of matrix B and then use that again and again. So it's called L2 caching of matrix B. And how why how does why is it important? Yeah, it just speeds up your computation because your all the columns are already in L2 cache and you don't want to reload it again and again. Okay, so in grouping now this is what happens. These are all the combinations of PIDM and N. So you see 0, 1, 0, 2. Here my columns are increasing when I'm going towards right, and when I'm going towards bottom, my rows are increasing. Now grouping is this idea. Okay, I don't want to do computation randomly. Like I don't want to go from 0, 0 to 0, 1 and 0 n. What I want to do is I want to group all the ones that have the same column. So here PIDN is 0, 0, 0. And in grouping, what happens is you take all of these. So for example, I'll take this tile which is 0 0 1 0 and 2 0, and then do the calculation, because for all these three tiles PIDN is 0, right? So that's the concept. As long as my PIDN remains the same, PIDN refers to the columns of matrix B, and so if PIDN is not changing, what that means is I have the same columns of the matrix B, and I don't want to again go to PID1, because then I'll have to reload all the columns of B, some other columns of B, right? So this idea that for a particular PIDN, you combine all the PID on the row side. So PID 0, 1, and 2, and then you do computation. Then you move on to 1, where here, right? So PID 1, 1, and PID1 and then PID2. So again, when I have PID1, I take all the PID along the row axis 0, 1, 2, and then you do the calculation. So rather than, I mean, overall, the computation is the same, the logic is the same. It's just that rather than moving, from left to right, you're just taking vertically, you're tiling it together, combining tiles on the vertical side and doing computation. And yeah, that is what is happening. And so, and also, right, so when you do this, you don't let's look at it in the code. And when you do this, you don't generate grid in two dimension, you just generate grid on the one dimension, and then you from there you generate PID MNN. I'll show that to you in the code. All right, so this is the code. I mean, this is again using our auto tune, but here is the trick. The input of I have matml kernel. Uh, Here, if you look at my program ID, it's only along axis 0. I don't have anything on the. So initially, if you looked at it, it was a two-dimensional M and N, right? So if you look at my this code here, I'm getting both of them, right? So, but in the grouping sort of matml, I just get one PID, and then from that one-dimensional PID, I'll calculate my PIDM and PIDN. All right. Yeah. So this I get PID along axis 0, and then from there I calculate my grid M light. So how many grids I am. So this logic is the same: grid on the x-axis, grid on the column dimension, and then this logic here is basically to generate PIDM. So you do all of this. You can go through the maths. You get PIDM, which is and then PIDN, and then once you get PIDM and then uh, and here is just to make sure it doesn't go out of bounds. So overall we should have grid M and grid N tiles, and I'm just doing making sure that it's the minimum of this doesn't go out of this. So yeah, this is only like little bit extra step in your group tiling, right? Apart from that, once you do this, all of this logic remains the same. This is exactly the same in normal multiplication, but in grouped multiplication, you just have to get the PID, which is a one-dimensional PID, and then from there calculate PIDM and PIDN. That's the only difference, and then the logic remains same. And why do you need to do that? It's just for L2 caching. It's optimization. That's it. Right, and then yeah, I'm defining here torch, blah blah blah, and then okay. The important thing is here when I call the kernel, you see here I'm just passing a one-dimensional grid, right? Earlier I had passed two, but here I get the grid m, which is initially in the first basic multiplication I had done grid m comma grid n here, but now what I'm doing here is I'm calculating, okay, how many tiles I have along x-axis, which is grid m, right? M by 64. This and then again on the column size n by 64, so I get grid m, and then I'm doing, okay, my total tiles have to be grid m and grid n. I'm multiplying that and passing that here. So overall I have the same number of tiles, but the way they are being calculated, like in the kernel, is a different. So rather than going from left to right, I go from top to bottom. Okay. Once I get this, everything else remains. So I just run it. All right. So yeah. So this is the output is the same. Now this maths that you saw here, right? How does this work out? If you want to see that from, okay, if I have the PID and from there how do I generate PIDM and N? This is what you. This is how you can see. Right. So I have just for example, let's say I have M is equal to 5 and N is equal to 3. So I'll have like grid M is equal to 5 and grid N is equal to 3. I'll have 15 PIDs, right? So overall 0 to 14, and then this is the math that you saw there. You can, and then eventually I'll have PID and PIDN of the 0 0, right? So for 0 0 1 0, and you can see here for I'm going from top to, so for n, when my here the group size is 2, so group M size is, I'm grouping in sizes of two tiles vertically, and then again the next two tiles, and then the next two tiles. So here for a PIDN, I when PIDN is equal to 0, I take the PIDM 0, then again the second one, because there are two groups, then I increment the PID one. Again, this is now 1 1, and then again for PID 1 I take 0 and 1. So yeah, basically 2 2 on the vertical side, then I'm incrementing the PID one. Similarly, when PIDN is equal to 2, I take 0 and 1, and so on. Okay. All right. Thanks. I know some of it was a little complicated, but I hope it helped you. I'm going to push the code to the GitHub. Thanks for watching. See you again.